All right, well, sometimes the forces are functions of S, and we may have to do some integration. So here's a little example problem that we can try to discover some things. Kind of clever, I believe. But let's say we have a box that's sitting on the table, and we're going to pull it up with over this pulley with a force with some tension, and we're going to call that tension a constant. And what have I got here? So let's draw a free body diagram. I'm going to say I got an mg coming down and a normal force pulling back up, and I got a friction force going in this direction. I'm going to pull this with some angle theta, and I'm going to go through some distance s. All right. I'm going to put that pulley up there at a height h, and we'll see how we can manipulate this. First of all, we know we're not going to be well, let's make sure we got our x's and our y's, get our reference frame here. So we know we're not going to be accelerating the box in this direction. So first thing I can do is sum of the forces in the y is equal to 0. And I'll say that I've got a sine component. The tension is going to be pulling up this way, so there's a sine component here. So I'll say T sine of theta minus my mg plus my normal force is equal to 0. And I can solve this for normal is equal to mg minus T sine of theta. All right, now that's kind of an intermediate result we'll have to refer to in a little bit. The force of friction, because it's slipping, is going to be equal to mu normal. All right, so again, we know that. What else do we know? I guess maybe we should start now with our energy equation and see if we can make some headway. What we're trying to find is the speed at the end of some s. So v equals something at the end of s. So let's say T1 plus V1 plus U non is equal to T2 plus V2. All right, again, V's are going to be my potential energy. My box isn't changing elevation, so both of those terms are going to be equal to 0. I'm starting from rest, so my beginning kinetic energy is equal to 0. So that puts us to U non is equal to T2. All right, T2 is going to be equal to 1/2 mv squared, which is basically what we're looking for. So my question here is, how do I resolve U non? Well, U non is equal to the integral of f ds, or let me put the sum of all the forces. So I should put, let's do it this way. The integral of the sum of f ds. Put the sum on the inside. So we'll add all those forces together. In order to figure out how to approach this problem, you have to recognize that the tension here pulling up is a function. The tension is going to be constant, but what's doing work is the cosine component. But that cosine component is a function of that theta. Also, the normal force is a function of theta. In other words, normal force gets lighter as theta gets bigger. The pulling force gets less as theta gets bigger. So there's definitely some interaction here. So we need to find S as a function of theta. That's kind of our big question. All right. Well, if we do that, I think we can look at our trig here, and we can say that there's an angle here and an h and an s on this side. So can't I say that tangent theta is equal to h over s? And if we do that, we can say that theta is equal to the tan minus 1 of h over s. And now we can use that relationship to our advantage. Let us complete our energy, or our U non equation. So U non, again, non-conservative forces are pushing, pulling, and friction force. I'm going to say that this is the integral from 0 to s of my forces. So what have I got? I've got a T cosine going in that direction. So T cosine theta, and it's going to go ds. Now let's put all the forces in there. T cosine theta pulls it this way. What have I got pulling back? I'll say minus force of friction, and both of those are through ds. Okay, let's keep on going. This is equal to the integral from 0 to s of T cosine theta. And here I can put my substitution in here. Oh, sorry. instead of theta, I'm going to put this cosine of my definition for theta, which is tan minus 1 h over s, minus my force of friction. Force of friction is mu normal, so that's going to be mu times the normal force of mg. And this is minus, and that's going to, then that'll be plus mu t sine tan minus 1 of h over s. And all those things are then integrated through ds. Okay, so that looks a little hairier than perhaps I would want to do by hand, but using your calculator you can easily plug this into your calculator and find an expression for, or find the value of u non when you integrate from a particular s, when you put some real numbers in there. Okay, well I hope that gives you some insight on how to approach some of these problems, and we'll do some more in class.